looking at model learning and self-supervised learning in the last lecture. So in this lecture, we'll continue with looking at self-supervised model learning. We will do the case study of flying. Then we look at inverse models. Then we look at goal conditional RL. Then we look at a case study on combining analytical models with learned models. There are some advanced topics which we won't be able to cover in this lecture, but I'm mentioning it. I think we'll be covering some of it in the last 3 lectures, which are specifically earmarked for advanced topics. So, so in the previous lecture, we saw, a case study of self-supervised grasping, and we also saw self-supervised pushing, right? So now let's look at another case study, which is a flying over here, right? So what we want to do is to have this drone, fly in the, in indoor environments. So how we might go about doing this. So one possibility is, you have this drone, bump and move around. It's collecting its own data. It's also bumping into things, right? So essentially what it needs to learn is what are obstacles and what are not obstacles. Now, if this drone has, touch sensors on it, which can feel the impact when it hits an object, then it can collect its own data set, right? What it says is that given a particular observation, if I take the forward action, would I crash into something or would I not crash into something, right? So this helps me learn what things are obstacles and what things are not obstacles, right? So how does it happen, more concretely? This drone has a camera over here, and it also has some, touch sensors which tell it when it, hits the object. And, so what are positive data points? Are data points where the drone, moved forward and it did not, end up running into any obstacles, right? Then, there is some data, which will come into what is ignored data. And then there's some data which is negative, when you actually hit the wall, for example, right? So typically so you saw that initially there was some positive data, and eventually the drone crashed into a wall, and that made the negative data. And we left the data in the middle. It is, quite common to leave data which is at the border of transitioning from positive to negative. And, a popular way to do it is to just leave some time window so that you don't end up confusing what is positive and what is negative. Now, this is not, like a significant point of how do you choose what part to ignore. This is more of a practical implementation concern, and this is task dependent. So if you're more interested in this choice, I would recommend reading this paper, whose reference is on the bottom of the slide. I think the main takeaway is how we can leverage sensors on the robot itself to label what is an obstacle and what is not an obstacle. And we are going to use this data to learn a policy which allows my drone to fly around in indoor environments. Okay? So essentially, by doing this data annotation, we have positive data points and negative data points. And overall, they collected 55,000 images of positives and negative data points. And how are we going to train? Seems I'm getting an echo from someone. Not sure where, but okay, maybe it's better now. So what do I need to do, right? At test time, I'm given an image, and I pretty much need to decide which action to take, right? So so the way, okay, so let's see, how this would happen, right? At test time, I would feed in, the image, and, I would see whether my prediction is that I'm going to crash or not crash, If my prediction is that I'm not going to crash, then I'm going to move straight. If my prediction is that I'm going to crash, then I'm not going to move straight, right? Then what I can also do is, I can crop like the left part of the image and the right part of the image, right? So suppose a prediction came out that I cannot, move straight. Then there are two possibilities, that either I could go left or I could go right. So I can take the left crop of the image and then pass it, and again get the same prediction, straight or not straight, and the right part of the image and get a prediction, straight or not straight, right? So the right part of the image comes out that I can move straight, then I can command my robot to move right, right? Versus if the left part of the image comes out with a prediction that goes straight, then I can move left, right? So pretty much think of what this network is learning like a Q value, right? Almost. It says, given the image that I'm feeding in, can I move straight or can I not move straight, right? That's all that we are learning. So is this clear or is this confusing? Right? I can just recap this once again, right? So we have this data that we collected. Given an image patch, I can say if I move straight, am I going to crash? Am I not going to crash? Right? I use this data and I train a network which, given the image, predicts a crash or a no crash. I've trained the system. Now I want this drone to fly. So at test time, I end up getting this image. The first thing I'm going to see is if, does the prediction say crash or not crash? If the prediction says not crash, I can move straight. If the prediction says crash, then I cannot move straight. Right? That means either I should turn left or I should turn right. How do I decide between those two? Right? So if I were to turn left and I'm not going to crash, which that means that if I crop the image on the left, then my network should predict I should be able to move straight. Right? So what they do is, they would crop the left part of the image and the right part of the image and test, whether I could move straight in either one of those directions, right? And depending on that, I could either turn left or turn right. So that's how I can use this model, right? Yeah, so I think this is, as pointed out in the chat, it is exactly like training a 3D depth predictor, but without requiring 3D, right? So, that's the whole, story of self-supervision, that you can, train things with very simple sensing or heuristics, which would do something which would require much more heavy sensing machinery, for example, a depth sensor, for example. So let's look at how the system ends up performing. So this is the test time run of the system based on the idea that we just discussed. I think one of the cool things was that even though these things are transparent, like the doors, the system does not confuses it with door like free space, right? So if you have a depth camera, like many times it can confuse glass as free space. So okay, so one question which has come up is this learning online? No, this is learned offline. And so initially you collect this data set, you have your model, and then you're just deploying the model. I guess another question is, how do they crop the scene? Ayush, do you have a specific question on this?
Yeah. On this slide, so basically, if you give this image, there are actually two hallways that the drone could go into. But but there's like a wall in the middle. So it's like, what does straight and what does right or left really mean? So it's like, ideally, we need some sort of a detector to identify that there are two candidate hallways that you have to pick between.
Yeah, so this is not what this is doing. It could be any image. I can do three actions, that either I can go straight, or I can go left, or I can go right. Right. And I'm just trying to choose between them. I'm not trying to do global navigation over here.
Okay, so it's like when you're looking at this image, like what action do you take? It's like,
okay, so good question. Right. So first thing I'm going to test is, if I take a straight action, am I going to crash or not crash? Right. So this is what these two nodes will predict, right? Because that is how I trained my network. with my data set. So if my crash probability is low, then I'll just go straight.
Got it. Okay, so what I'm really confused about is what does really going straight in this mean? Because it's like I could go straight. It basically depends upon like my orientation. I could go straight into the left hallway, the right hallway, or the wall in the middle.
So orientation, just think of it that you have your eyes, your camera is facing straight, right? So going straight means you will just move towards whatever is the center pixel in the image, right? So maybe over here,
Okay.
where you will go towards, right? And as you come close to this wall, then you would choose to move left or right.
Got it. Okay, so it's like if you go straight and you crash, then you split the image about your center point.
If you predict that you're going to crash, right? You don't have to crash
Okay.
at test, right? At test time, you don't want to crash. At training time, you have crashed enough, right?
Got it. Oh, okay, yeah, that makes sense. Okay, so it's like if you predict you're going to crash, then you split the image by the middle, since like you were targeting the middle and you made that prediction for that point.
Yes.
Then got it. Okay, thank you.
And that will tell you whether you should go left or whether you should go right.
Okay. Yeah. But like I had another question, like it's probably already incorporated, but like don't you think like really estimating like the 3D geometry of the scene would help? Because you don't like we are able to perceive navigation because we understand like there is a pathway we have to walk through. Like it could just be a poster as well on the wall.
It could be, right? So it's a great question. Can we, if we could perceive the 3D structure, would it help? The answer is yes, it would help. But then if you have a drone, you have other constraints, like your battery constraint. You have, your sensor is going to be heavy, which is going to reduce the battery lifetime, right? So you want to do as much as possible from cheap sensing. And this is what this research is showing, right? And it is not saying don't use good sensors when they're available. All this is showing is that with very cheap sensors, we can do a lot.
Right. Okay. Okay. So that's like, but they don't really estimate even depth, like with like a simple.
No, just a simple RGB image.
Okay. Thank you.
So there's no IR sensor either, right?
Yeah.
There's no IR sensor, it's just an RGB image.
Got it.
And I mean, you do get some benefits, right? For example, if you had an IR sensor, if you came across a glass wall, the IR sensor is not going to work. The light is going to go through.
Yeah.
Right. So training from images does have some advantages also. Now, depending on what your problem setup is, right? Maybe, the kind of motion they're showing is, quite slow, and maybe it does not fit your bill. But I think the point of this work is not to say this is the best way of flying drones. I think the point of this work is to say, even if I have very cheap sensors, there's a lot more I can do than what you would think initially. Right? That's what they're trying to show.
Got
and
it. Thank you.
And then and I think then they have like these videos of people moving around, and drones kind of going around them. So if you want to look more, you can read this paper up. But I hope I communicated the main insight over here of how they're leveraging this touch sensor, which is a hit sensor, and camera to learn how to navigate somewhat without requiring explicit estimation of depth.
Thank you. Yeah, I got that. Thanks.
Cool. Any more questions over here? How is this different from reinforcement learning? I mean, reinforcement learning is, just a term which means that if I have rewards, then I'm going to use the reinforce algorithm to optimize those rewards. Right over here, you're not really using the reinforce algorithm. Right, you are converting the reward signal into a supervised learning problem. Right, because you're just predicting whether I'm crashing or not crashing. You're never explicitly estimating, what your reward is, or taking, Yes, I mean, so you get a 1 or a 0 reward in the end, but you use it to do supervised training, right? You said this action is a ground truth, this action is not the ground truth, right? So using the reward as a labeling strategy to do supervised learning, right? You could, in an alternative world, do PPO, but in PPO, your reward function, may not be differentiable. So you'll have to use reinforce to estimate your actions, which might be much more data inefficient, right? So if you could use your reward to annotate which actions are correct, then you have a big win, right? Because if you think about in reinforcement learning, if I have n actions, I don't know which action is a good one. I have to try all of them to figure out which one of them gets a high reward, right? And that is what leads to sample inefficiency, right? Over here, they could say this action is a good one, this action is a bad one. Does that make it clear? The distinction between just doing reinforcement learning and supervised learning? No, I feel there's still a question over here. No. Okay, how about we take this up in my office hours? If you're interested, come and we can discuss much more in detail. Okay, so let's move to the next part of this lecture, which will focus on inverse models. Now, we have seen inverse models in some form in the imitation learning lecture, but as motivation for why should we consider inverse models, let's go back to what we were talking about, right? Building forward models. Forward models are things which say, given my image and my action, predict what is going to be there in the future. And one choice that we saw was where we make the prediction pixel by pixel. So let's expand upon this box, how it might look. I might have my image X, which I encode through a network to some representation Z. Then, I'm going to combine my representation Z with my action to get the representation at next time point, which I'm then going to decode to produce image xt plus 1. This is how I can train my forward model. Then, what did we see in the previous lectures was that we can use these forward models to infer a sequence of actions, right? So this is the optimization that we posed. So one thing I would like to re-emphasize is that we care about the action sequence. We really don't care about the forward model. The forward model is just a tool or a convenience which helps us infer the actions, right? That is not our end goal ever, right? The end goal is to get a sequence of actions. So, one thing or one question you can ask is, these forward models, because they try to predict things precisely in the future, they're hard to learn. And maybe, we are trying to learn way too much, right? For example, if you're playing a game of tennis, right, you just need to know how to hit the ball, right? You don't need to always imagine, how the ball is going to move throughout the entire trajectory, right? So is it the case that we are trying to learn or solve a much harder problem, right? For this, provides you with an alternate perspective, right? I mean, as was put by this guy, Vladimir Vapnik, who created SVMs or support vector machines, if you have heard that term. And he says, when solving a problem of interest, do not solve a more general problem as an intermediate step, right? The point being, what we're interested in is inferring actions, right? Maybe we don't really need to solve the problem of forecasting how the world is going to evolve necessarily to infer the actions, right? So, what could we do, right? I mean, one thing we could do is, we can try to directly predict the actions, right? So I can say is, given my image xt and xt plus 1, let me try to predict my actions at directly, right? It turns out, you can, pose this as a prediction problem, right? And, for example, if you take data from, self-driving cars moving along, and you have image taken from the self-driving car at some point, and at some other point, or not self-driving, but any car moving around, and you can try to predict your self motion. Right? Turns out by just doing this prediction, you can learn these which are useful for doing image recognition, pose matching, and so on. Right? And so this idea that I can correlate two sensory modalities that I have, right? So in the drone example, I was correlating my vision with my touch sensor. Okay, over here, I'm correlating images with my own motion, which is something I can record. It led to a line of work which came to be known as self-supervised feature learning. Right? For example, there were many metrics people came up with, or many cross predictions people came up with. For example, people would take the image as input and predict the audio, right? Or they would take an image of a bus and crop it into say 9 pieces and say, given patch 1 and patch 2, can you predict what is the relative orientation between those patches? Or they would start off with a black and white image and try to predict the color image. And so if you think of all of these examples, what is happening is you take one sensory modality and then you try to predict a different sensory modality. And what you're hoping is that by making that prediction, we will learn a useful representation. Right? So sometimes, the other sensory modality can be low dimensional, right? For example, if I am predicting from these two images, I am predicting the actions. Actions are much more lower dimensional than trying to predict the overall image, right? Or for example, if I take this image of a bus and crop it into 9 bins and try to predict the relative orientation of the patches, this is again a very low dimensional prediction as opposed to reproducing an image of a bus at the next time point. Right? So, one thing you could do is you could take any of these methods. Over here, I'm going to focus on one of them, which is predicting the action. And you can learn some useful features. And then you could learn a forward model in this feature space. Right? So this could provide you an alternative to doing pixel predictions if you were to build forward models. And if you are predicting the action, then maybe you can just use this action to transform the world from xt to xt plus 1, right? You may not need to use the forward model and then infer the action, because I'm directly predicting what is the action I need given my current image and a future image, right? So I condensed two things, two ideas over here. Maybe this was a little too dense, right? So one idea is, do I really need a forward model? It's an open question. One alternative is I take my current state and my goal state and directly predict the actions. Right? That is one set of ideas. And this model, which takes pairs of observations and gives you an action, is the inverse model. Right? That's how we are defining it. The other set of ideas is that if I were to learn a forward model, I don't need to do pixel prediction. I can leverage other tasks to learn a good feature representation. For example, a task could be to predict the action, or it could be any of these tasks that I briefly mentioned over here. Like I could predict the audio, I could try to predict the color image from the black and white image, and so on and so forth. Right? And then I could learn forward models in a better feature space. Right? So this is something, how do we learn forward models in this feature space, and how do they turn out to be better than doing pixel prediction is something we are going to see in more detail in a future lecture. What I'm going to focus right now is just on the inverse model. but something to keep in mind, right? So now, for example, I can, take this, say a system, which was, say pushing objects. For example, I have this robot has an image xt as input, it executes an action, and then I get my next image, right? So in the previous lecture, what we saw is how we can leverage forward models to push objects. In this lecture, we'll start off by seeing how we can use inverse models to push objects. So how does the data look like? I have my image before and my image after, right? And and I know the action which the robot made. And the question we can ask is, is this robot able to learn a good enough model, which if I give it a start image and a goal image, it can produce a useful sequence of actions, right? That's how we're going to test the model. But before, before I go into this, right, I'll just pause and see if there are any questions. So Ayush, you have a question. Context tasks are doing pixel prediction still. So there are some context tasks, Ayush, which do pixel prediction and some don't do. For example, there's a line of work where people take out a part of the image, then they try to reconstruct the image that was taken out. But in other tasks, what they also do is, like I was showing, they can break the image into 9 parts and say, can I pick the relative location between 2 image patches, which is still figuring out the context, but without explicitly doing pixel prediction. Does that clarify? Okay, cool. Any other questions over here? So I am not sure what you mean is the action here, push 3D pose. The action over here is, what is the position where you want the gripper to start and what is the position where you want the gripper to end, right? That is the action representation over here, right? It's a x comma y position, or you can say x comma y comma z position if you want to be more general. The start position and the end position, and the gripper just makes a motion. Okay, so how should we go about testing the model, right? So one thing I can do is I can take this initial image, I can take a goal image, and I can ask the question, what is the action I need to predict, right? However, if my initial image and my goal image end up looking very similar to my training data set, right, then even if I can perform this task, it wouldn't really tell me much, right? Because I could just have overfit to my training data set and still have performed this task. Right? So to know if you have learned a good model, we would like to generalize to scenarios that we might not have seen in the training set. Right? So for example, one thing I can do is I can take initial and the goal image in which the object is displaced by a very large amount, maybe even so large that one single push cannot take the object from the start to the goal. So we necessarily require a sequence of actions over here, right? Or we can ask the question, can we push objects that were not there in my training set, right? Can we displace previously unseen objects? Okay. So if we were to solve these tasks, then one question you might have is, well, in the training set, my image xt and xt plus 1 were only displaced by one action. But if the test set requires me to produce a sequence of actions, then what do I do? Right. So we're going to start with a very simple strategy and then build on to more and more complex strategies. So the simplest strategy I can do is I'm going to say, well, I'm going to take my initial image and my goal image and not worry about that the goal image is out of distribution and just predict the action and execute it, right? Now, if I was able to extract good representation of the environment, then I might be able to predict a good action, right? For instance, if I was able to identify the location of the object, I might still say push to the right? Versus if I picked up on wrong features, then I may not be able to make the right action prediction, right? So I can predict one action, execute it, I get the next image, then I feed in this next image and my goal image, and then I iteratively keep on repeating this process till the time system says I am close to my goal image. Right? So this is similar to what we discussed with the forward model, right? Where we're doing the cross entropy method. We would come up with a sequence of actions and evaluate if that sequence of actions is going to be good or not, and then choose the action which we thought would get us closest to my goal state, right? Over here, instead of doing that search, I'm going to just take my current image and my goal image and directly output my action and repeat this process iteratively until I think I'm close enough to the goal image, right? So in the first part, right, although we are training the models for single step, we're going to use it for multi-step decision making, right? Now let's see, if this actually ends up working. So, turns out that in some scenarios, this can actually work. For example, over here, the system is, trying to push, for example, this red cup to this goal location, maybe it requires a sequence of actions to do it, and the system might not have seen, those cups in the training, right? Similarly, like this object over here. So, what is the takeaway? I think the first takeaway you can have is, in the last lecture, we discussed how forward models can be used to solve this task. Now what we have seen is that we could also use inverse models to solve this task, right? Okay, now, but the task that I have just shown you, right? I mean, maybe this pushing task is, maybe somewhat I mean, you can think of it, some of you might think it's a simple task, because I just need to push an object, right? If I pretty much get the initial location, the final location, and then if I make the right contact, I should be able to push, right? And then you can say, well, what happens if I go and try to solve a more complex task? For example, if I give you the rope in this configuration, I want to go and tie a knot, for example, right? So again, we can follow the same scheme that we had before, that the robot will now interact with this world and collect its own data, right? So over here, the action is, there's a pick. So there's a pick location, which is a 2D location on the table. And then the robot goes and places the rope, right? So it has a place location. So again, my action is a 4-dimensional vector, x1, y1, x2, y2, right? And I can collect my images before executing the action and after executing the action, right? And I can use that again to learn an inverse model. Right? Now, I could, pose the task and say, well, given this current image, can I go and, tie a knot over here? And I'm doing this purely from RGB images, right? And, it turns out that, if you pose this as a problem, the robot can perform, this particular task, at around 18% accuracy, right? So what we saw, in the previous lecture was, if we used these inverse models with imitation learning, they're able to perform much better, right? Right now, what I'm just showing you is just the inverse model performing the task that I gave. Right? So in summary, what we have seen is that if we are collecting data in a self-supervised way, then we have seen two methods, the forward model and the inverse model, which can help me perform downstream tasks. So now I'm going to take a small break, on a small pause, and see if there are any questions over here. No. Okay, so let's move ahead. So this is what we had seen in the previous lecture, right? That if I was trying to imitate a human demonstration where I only had access to observations, how we could use the inverse model to learn from this video demonstration, right? That is what we saw in the previous lecture. And if you did imitation learning, you could increase your accuracy to around 26%, but we'll see how we can increase it even more to around 60%. Okay, so what we have seen, I think just to summarize again, right, that models that we are learning from data can help us perform some downstream tasks. Then, if I'm willing to get some more supervision, for example, watching an observation of how a human performs a task, we can leverage models and improve our accuracy, for example, from 18 to 26% over here. Now, how this is being done, go back to lecture on imitation learning, where we discuss how exactly to use the inverse model to do imitation. So one question which has come up on the chat is, if the robot is collecting data freely, wouldn't it be data inefficient? Right. So I presume what you mean over here is to say the robot is performing a sequence of random actions. Would it not need to collect a lot of data? The answer is yes, it does need to. For example, in these examples, the robot collected around 50,000 data points, right? So, this is not, like 1 million or, 10 million, which is much more usual to RL, right? It is still much less than what you would find with a reinforcement learning system, but there's still a lot. Now, there is research which is ongoing on how you can make the data collection be more efficient, something we will look into in the lecture on exploration, which is, I think, a couple of lectures in the future. Okay. So now, let's build upon the inverse models for a little bit. And we're going to build upon the inverse models because this is going to lead us to goal conditioned reinforcement learning in some time. And that is something which I think everyone should know about if you want to know about reinforcement learning. So let's consider the inverse model. I have my state st and st plus 1. I'm trying to predict an action. The way we do this is to pose this as a supervised learning problem where I have parameters theta g of my inverse model, which I'm trying to optimize to match the ground truth action. Or we could also have a forward model, right, which takes the state and the action as input and predicts the next state. And I can write the forward loss function. And instead of training any one of these models, I can train both of them jointly, right? I can learn both a forward model and an inverse model. But now let's look at this particular loss function. Suppose I have my state st and st plus 1. Now there can be multiple ways to go from one state to the other state, right? So now suppose my prediction is a hat t, but my ground truth is at. That means I have achieved, I will go to the correct state, but the inverse model is going to have a high loss. Right? This is why is this? Because there's multimodality in the action space. That is, there are many actions which can take you from one state to the other state. Right? So this is bad news for inverse models. And right now we're just talking about a single action. As we increase the action space, just not to be a single action, but a sequence of actions, this multimodality problem will become even worse, right? Because the number of possible action sequences which can take you between two states is going to grow almost exponentially with the length of the action sequence. So what we're going to now look at is, how do we solve this multimodality problem? And we're going to look at a couple of different methods. Right, so let's start with first of them. So the first of them is actually going to leverage the forward model to resolve this issue. So in a forward model, if the forward model trained well, then if I input the ground truth action and my state st, then I should predict s hat of t plus 1, which should be close to my ground truth, right? But what about if I inputted an action predicted by the inverse model, right? Now, because this action a hat t might not be in my training distribution, I might not expect s prime t plus 1 to be close to st plus 1, right? But we know that if a hat t is actually correct, right, then s prime t plus 1 should be close to st plus 1, right? That is something that we know. So what we can do is, we can enforce this constraint, right? We can say, well, my inverse model is going to predict an action a hat t. And what I want is that this predicted action should also, when put through the forward model, should also lead me to the correct state, right? So I can add this additional loss term. Right? So what I'm saying is, if I have a hat t and at, instead of doing just this loss, if I put a hat t or at through a forward model, both of them should lead to the same prediction, right? For the forward model over here can help us mitigate this multimodality problem. So by training the inverse model with help of the forward model, I can get rid of this problem. Now, when you can, yeah. So this loss was referred to as, like the forward consistency loss in, one paper a couple of years back. Now, it turns out if you are willing to improve the inverse model in this way, then on the rope time task that we saw, you can improve your accuracy, from around 26% to 65%. What this means is, that multimodality was a big issue when you're trying to train inverse models. And if you're able to fix it, then it can lead to significant performance improvements. And now, because we can fix multimodality, instead of predicting just an action sequence, we can go, to just to predict a single action, we can now extend the model to predict a sequence of actions. How do we do this? We do this by, instead of having a feed-forward network, now I can put something like a LSTM or a recurrent neural network. The kind of models that we talked about in the deep learning lecture some time back. So now instead of predicting one action, I can also start predicting a sequence of actions over here. Now, let's see, how well, I'm just showing one more application of the same idea in a different domain. Here, this robot is collecting data, moving around in the office space. And again, it has this camera, it's an RGBD camera, but it only captures, RGB information. And it learns this, forward and inverse models. And now we're going to give it a task that, given the current image and the goal image, output me a sequence of actions so that I can go from my current to my goal image. So now suppose that you are in a new floor or a new building that you've never been to before, right? You don't have a map of the environment, and all you have is access to, RGB images, right? The current image and a goal image. So what are we going to do in this scenario to navigate from the current to a goal image? Any suggestions on what you might do? So if I put you in this environment, I suppose you were staring at this gray image, and I give you one more image which showed this couch, and I say, go over there. What would you do? So one suggestion is move around, one suggestion is move back, look around, right? So you would want to move around or move back and then locate where the couch is and then go towards it, right? So now let's look at, what the system does, right? Now it ends up, maybe locating the couch and then, moving towards the couch, right? So, how was the system trained? In the same way that we train the model for pushing or for rope manipulation, right? We collect this data, which is xt, at, xt plus 1. We train the forward and the inverse model, and then we just execute the inverse model, right? Now, the thing to note over here is that, we never told the system that it needs to go around and move around and then go and find the goal, right? This is something which emerges from the training automatically, right? So this is again, showing the kind of things that we want to do with models, right? We want to really extrapolate to new tasks that you may not have seen during training, right? So that's the whole point of trying to understand the world by building models. Right? With that, I'm going to take a 5-minute break. I think some of you mentioned in your feedback that it would be nice to have, a small break in the lecture instead of, going, in one go. So I'm going to take that suggestion and, take a 5-minute break. If you want to, so it's like 9, it's like, we'll start in 5 minutes, dot. Right, so I'm happy to answer any questions, if they are there, or we can just be silent. So 5 slides before, what does the goal setting, what do you mean by goal setting for success rate? So maybe you can ask me this question in office hours, I'm happy to answer. I'm not sure what you mean by goal setting over here. Okay, okay, the 5 slides before I can go to it. This thing, or goal setting. So remember in the imitation learning lecture, in the last part, what we discussed is how a human could provide some images where it wants the robot to explore. Do you recall that I could give it a few images and bias the exploration? So which is what I mean by goal setting. So your question initially was, if my robot is doing random exploration, that can be very sample inefficient, right? So one way to improve it is to have a human specify a few states around which it would be useful to explore, right? And that is what we saw in the imitation learning lecture in the end, right? So if you collect data with that in that setup, that is what is called as goal setting over here. Does that make it clear? Okay, perfect. Okay, so back to our 5-minute break. I'm going to shut off my video for a couple of minutes and then switch it on in 3 minutes. Okay, so let's restart, where we left. I think we have taken a 5-minute break. If still want to switch on your video, I recommend you please do. It is always nice to see faces. So, okay. So what we have seen is, this multimodality in the action space of inverse models, and we saw how forward consistency loss was able to resolve this. Now, the other thing we could do is to model the action distribution. So if you are familiar with models like variational autoencoders or other probabilistic ways of modeling distributions, you can use that. Something we will look briefly in a future lecture. Or you can use reinforcement learning or rewards to resolve this multimodality issue. So that is what we're going to focus on now in this part of the lecture. This connections between reinforcement learning and inverse models. So one of the very initial papers in this area was from Leslie, almost 30 years back, right? So now recall how Q-learning works. Q-learning is, I want to estimate my optimal Q function, which I've written down the bin update. And we also looked at how to update my Q function, right? Where over here alpha is a learning rate. Now, notice in the Q function, it only depends on the state and the action. It does not take goal as an input, right? What this means is that the Q function is with respect to a single task, which is defined by the reward function that we have. Right? The reward function is capturing one task. But what if we want to do many different tasks? Right? So what this paper suggested was to define a function, which is they were calling DG, because they termed this as dynamic goal learning because the goals could be changing. And what DG captures is the number of steps it takes to go from the current set to the goal, right? So if my current state is a goal state, then my cost is 0. Otherwise, I can use the Bellman update to compute what is the shortest path from S to G. Right? So think of it, that my reward function is the number of steps to the goal, right? Or the cost function, which is the negative of the reward function. And we can do DG learning, which is very similar to Q learning, and learn a policy which can go from any state to a particular goal or to a set of goals if I were to define them. Right? Is this setup clear? Any questions about what is DG over here? No? Okay. So this paper also had one more suggestion on how we could make this DG learning be computationally efficient. Right? And this was based on a prior knowledge that we know something about distance metrics. Like for example, they satisfy the triangle inequality. And what do I mean is, if D of S1 comma S2 is the shortest distance from S1 to S2, then this equality holds true. Right? This is true for any distance metric. Now, we can leverage this because what we could say is, while I'm estimating my value D, I can sometimes, what could happen is that my estimate that I have, I could think that it takes me a lot more steps to go from S1 to S2 than it takes me. So I could, say, well, DS1 to S2, either I can keep the current value, or let me see if there's some other path I can find which takes me shorter number of steps to go from S1 and S2, right? So I can take the minimum of my current estimate of how far away the state S2 is from S1, plus maybe if the estimates of S1 comma Si and Si comma S2 are better, maybe I can, I'll get a more realistic value of this distance function. Does this make sense? Why we might do this operation? And the suggestion was that we can interleave DG learning with this relaxation step. Right? So we do some iterations of DG learning, and then we do this relaxation step. Right? Now, what's the advantage? The advantage is, like in Q learning or in DG learning, I'm always propagating Q values by one step, right? Given this state ST plus 1, I propagate it to ST, then to ST minus 1, then to ST minus 2, right? So it is a very sequential process that happens. But by this relaxation step, I can propagate values by multiple steps at once, right? Because my state Si could be arbitrarily be far away from S1, right? So I don't need to propagate my Q values one step by one step. Right? So it allows me to propagate values, by long chunks, right? Which is why this relaxation could speed up learning. Right? So just think of it in dynamic programming, right? You go to the end and you use the end to propagate values to your starting state. But somehow if you can skip the queue, right, and propagate the value from the last state to say the middle state, and middle state to the first state, then your learning is going to be much faster. Right? So the relaxation step is kind of doing that. Does the intuition behind relaxation step, is it clear? Any questions over here? Okay. So now, but it turns out that doing this relaxation step is actually quite challenging. Right? And the question is, why is it challenging? Now, why is it challenging? It comes from a fact about some properties of DG, right? And instead of answering this question first myself, I have this poll which I'm going to launch, right? And the poll says, for the relaxation step to be useful, the estimate of DG S1A comma S2 should be optimistic, pessimistic, or doesn't matter. So what does pessimistic mean? Pessimistic means that suppose if I were to take 5 steps, then DG overestimates and say I take 10 steps. Right? That is being pessimistic. What does optimistic mean? That suppose if I have to go, if my actual ground truth distance is 5, I think it is 2 or 3. Right? That is being optimistic of how far away something is. But the question is, if DG learning, or if the relaxation step is going to make my DG learning better, then should there be a certain property that DG S1, A, S2 should satisfy? Is the question clear? Right. So, maybe there's something to process, in this question. So I will, give slightly more time than usual, maybe, 30 seconds to think and answer this question. And if something is unclear, feel free to, put it on the chat. Can you change your choice? Unfortunately, I don't know how we can do this. But you can tell, yeah, I mean, unfortunately, we can't do it now, but maybe in the future we can. Okay, so last 5 seconds, this, whatever you think, if you're on the fence, cast your vote. I think only 57% of the class has voted now. So don't be on the fence anymore. Make your choice. You're not being graded on this. It's completely anonymous, all this poll. Okay, 5 more seconds. Okay. Okay, so let's see, what people think. It seems like, there is, a fair mix over here where 6 people think that it should be optimistic and 8 people think it should be pessimistic. Right. So does someone who think it should be pessimistic, say why it should be pessimistic? Because of a main operation, it's a heuristic. Right. So it should be pessimistic. And the reason is the following. See, when will this main operation be useful? So if I'm optimistic, then I'm always going to choose dg s1 a comma s2. In that case, I will never update my value of dg. Right? The only time I'm going to use this term on the right hand to update the value of dg is if I am pessimistic. Right? So in order for this relaxation step to work, my estimates need to be pessimistic. But on the contrary, if we want to do good exploration, this estimate should be optimistic, right? Because that is what we saw with bandits, right? That optimism in face of uncertainty was what gave us UCB as the algorithm, right? Which led to good exploration. So there's this trade-off between how DG should be. For good exploration, it should be optimistic. For this this jumpy propagation, it needs to be pessimistic, right? Which is what makes this interleaving tricky, right? So turns out this paper in 1993 did not really answer this question. It suggested this method and identified the problem, right? I think still, even now, when we do Q learning, we do it, we propagate things step by step. So if you come up with a good way of doing this, to propagate Q values by large jumps, that could be significant in how quickly we can learn the Q function or the DG function over here. Any questions over here? Okay, so no questions. I'll just say one takeaway. The takeaway is, if you know something about the reward function, right? For example, we know the reward function is a distance metric, right? And we knew a property of the distance metric, which is a triangle inequality, right? We could come up with a formulation which helps us exploit that information to do faster updates, right? But there are some issues which make it hard. But always think, if you know something about the reward function, you can do something more than the most standard. So the question is, how is DG related to the inverse model? Right, so in the inverse model, what are you trying to do? You are trying to predict the sequence of actions which goes from state to the goal, right? So this is, DG learning is trying to estimate a goal condition policy, right? And the Q function is now, so if you look at, the Q function, right? The Q function only depends on the state and the action, which means that you're only learning a policy which maps from states to action. In DG learning, DG depends on state and the goal, and you're trying to evaluate how good the actions are, right? So the inverse model takes the goal as input and produces a sequence of actions. Q learning doesn't take the goal as input per se. You can do goal condition Q learning, which is what they call as dynamic goal learning, right? Does it answer the question? Okay. Another question I'm getting is, are attention mechanisms possible for long time propagation of the Q function? Yeah, so there is work on this. You can look up this paper called Rudder, which is there, and there are a couple of other papers which look at how we can do long-term propagation of the Q function using different ideas than the one that we described. But attention mechanisms with some more stuff are definitely a good way. Simon, I'm happy to discuss this in my office hours. Okay. So let's look at another perspective on connecting RL and inverse models. Right? Suppose I have my state S1 and I want to go to state SD. Right? And what I want to do is to come up with the sequence of actions. Typically in reinforcement learning, I would want to maximize the sum of rewards, and I want to find a policy which does that. Well, let's define a reward function which says I'm going to be 1 if my current state is my goal state. Otherwise, we are going to be 0. Which means I can write my reward function as the probability that my last state is my goal state. Right? If it is true, then I'll get a reward of 1. And because I have a discount of gamma to the power t, I just have my discount term over here. Now this paper, planning from pixels using inverse dynamics model, what it showed was, if we use this as the reward function, then learning the policy, which is A given S, is akin to learning an inverse dynamics model, which is P of A1 to AT minus 1, given S1 in the goal, but weighted by a prior term. Which says, so let's, maybe to just state it again, right? Suppose if I collect some training data, right? So what we were doing in the previous part of the lecture was we were just estimating the term in the numerator, right? Which was P A1 to AT minus 1, given S1 and G. What this work showed is that if you want to find the optimal action trajectory, you should also divide by this term, which they call as a prior. Right? So how do I solve for this? I have my typical inverse model loss function, and I put another loss term, which just predicts the probability of a sequence of actions when I've not conditioned on the goal. That is why it's called the prior. Because this is saying if I was in state S1, if you didn't tell me anything about the goal, what would be the most likely sequence of actions that I'm going to do? Right? And the inverse model is saying if you told me that I have to reach state ST, then what is the sequence of actions I should do? And if I divide these probabilities, this will give me the optimal action sequence. So what this work shows is that if I assume a specific form of a reward function, then I can solve the RL problem by learning the inverse dynamics model and a prior. And they showed results on Atari games, and they showed results on the Mujoko control tasks. And I think what you should look at is the orange line, which is a goal condition supervised learning, which is the kind of inverse models that we were seeing before. And green is glamour, which is what they call their method. If the difference between glamour and inverse model is just this term, the prior term is included in glamour. Right? And they end up, being better than previous methods of doing, RL on these tasks. So you can, think of, glamour, as doing model-based RL, where the model is no longer a forward model, but it's an inverse model in this case. So in summary, what we have seen is, we can learn policies by SI given SG. Why would you want to do this? Because you don't want to learn a policy which can only achieve a single goal, but maybe at test time you want to change the goal, right? And therefore you want the policy to have this parameterization. When we tried solving with supervised learning, we found multimodality is an issue, right? Then one technique that solved this multimodality issue was to use reinforcement learning, right? Because all sequence of actions which have the same reward, so it in reinforcement learning, it does not matter which one you end up choosing. You can choose any one of them. So therefore, multimodality doesn't become an issue. Right? But the one advantage that the supervised learning had, that if I had any data points at S, A, S prime, we can use all this data to train my inverse model. But when I'm doing reinforcement learning, suppose if I have a tuple S, A, and S prime, where S prime is not the goal, that means I get a zero reward, which means is this data point is not really useful for me to update my policy, right? And that is what causes data inefficiency. That only a very few interactions which take me to the goal actually give me a positive reward. And I can pretty much only learn from those transitions. Does this point, is this point clear? Right? Because in supervised learning, I can always supervise with my action A. That's what I'm trying to do, right? S comma S prime, predict the action. But if I'm doing reinforcement learning, I need to get the reward, right? So if my next state is not the goal, I don't get a reward. If I don't get the reward, there wouldn't be any learning, which is what makes learning these goal condition policies with reinforcement learning data inefficient. To resolve this issue, there was a method which was proposed, which is called as hindsight experience replay. So let's discuss this paper now. But before we discuss this paper, are there any questions on goal condition policies and the comparisons I laid down if you try to learn it using supervised learning or reinforcement learning? Nope. Okay. So, okay, there's one question. So can you please explain why multimodality is not being an issue in RL? So in supervised learning, the issue comes because my ground truth, there is a ground truth action sequence that I'm trying to match with my predicted action sequence. So my loss function is on the action space. In reinforcement learning, the loss function is not on the action space. It is I'm trying to maximize the sum of rewards. Right? So I can arbitrarily choose any sequence of actions. Suppose if there are 5 sequences of actions which lead me to the same reward, I can choose any one of them and it's going to be fine, right? Because I never have to compare it with the ground truth action sequence. Till the time it maximizes the reward, I am good. Any more questions over here? Okay, so let's look at this paper, hindsight experience replay. Right? So this paper showed results on a set of environments. First, I'm just going to tell you the environments. So for example, I want to push this block and this is my current state and this red block is showing my goal state. Or if I want to slide this block or maybe pick up this block and bring it to some position. So these are all goal condition tasks where I have a goal and I have my state of the agent. Right? Now what's the main idea? Suppose I am in some starting state S0 and I want to go to the goal, and I define a reward function which says if I am within some epsilon ball, I'm going to get a reward of +1. Suppose I roll out a trajectory, right? My episode ends, I end up at state ST1. So we get this trajectory for the first rollout we do. Let's do a second rollout, we get a second trajectory. Right? Again, we have not hit the goal, so we have got no reward. Now let's do a third attempt, and suppose this time we get lucky and we do hit the goal. Our aim is to find this goal condition policy in ST, G. Now, typically, I would pretty much disregard these trajectories because they're not giving me any rewards, so they don't give me any gradients, right? So the main hypothesis of this work is, well, what if I learned a policy which was trying to actually go to the goal state 1, right? So suppose I ran this policy, I ended up at ST. Like I was trying to go to SG, but I ended up at ST. But now I say, well, imagine that ST was the goal that you were trying to go to, or ST1 was the goal that you were trying to go to, right? So now I can get a reward for training this policy, right? Pi theta ST plus 1 to ST1, right? Then the second trajectory, it also failed, but I said, well, what if my goal was to go to S2? Then I will be getting a reward for this trajectory, right? So in hindsight, after executing the trajectory, I'm deciding what my goal is, right? So therefore the name hindsight comes in, right? Now, why is this useful? This will only be useful if by learning pi of theta of these two things on the top, I will learn something about my actual policy, which was to go towards the goal, right? So what this is saying is in order to go from my state to the goal, if I also know how to go to some other points in this space, this would be useful to go to one particular point, right? So this is the main idea behind hindsight experience replay, right? And I think it's very well summarized in the comment made on the chat. This is like explaining away your failures as intentional lessons, right? This is exactly, what hindsight experience replay is doing. So what are we getting out of it, right? We are converting a very sparse reward signal, but by relabeling things as goals, we are able to make the reward signal be much more dense. And this is what we are gaining by doing this relabeling. So we can look at it, much more precisely. So I've just copied this algorithm box on the paper. So we're given an off-policy RL algorithm. So this will work for only off-policy stuff. Something to think about why that is the case. Then we have a strategy for sampling goals for replay, a reward function, and the usual stuff, right? Now, we have a goal and we have some initial state as 0. We have some estimate of the policy from which we sample actions, right? We sample T actions and we end up with the last state, right? We get my trajectory. Now, that we discuss in off-policy learning, we throw all of our experience in the replay buffer. Then we, sample data from the replay buffer and we use it for training, right? Which would be ST concatenate with the goal, RT, blah, 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 right? And this RT is going to be 0 for almost all the time steps, right? Now, what we're going to do is we're going to change this step by doing relabeling. And now what we do is we modify the goal G prime, right? We say, well, G is no longer my goal. My goal is going to be G prime. And I'm going to store this in my replay buffer also, right? And then there are different strategies that I can use to choose G prime, right? One strategy we discussed in the previous slide was just to take my last point of the trajectory and label it as a goal. So it turned out this paper, tried different methods of doing this, right? So they tried a couple of different methods. So one method they tried was what they called as final, which is what we discussed previously, which is you take the last state of your trajectory and call it as goal. And what we are seeing over here is, on the y-axis is the success rate. And on the x-axis, what they're showing is the number of goals that you label in a trajectory. Like in a trajectory, you could either choose to label only the last state as a goal, or you could have chosen other states also as a goal, right? For example, what you can say is, given my current state, the state after k time steps is my goal, right? Which is what they call as future, right? Or, you could be, you can say I'm going to choose any k states, states in my episode and call them as goals, right? So there are others, so you can look at the details, but turns out the strategy which works best is the future strategy, which says, let me pick a goal which is k steps in the future. That instead of just choosing the last state as my goal to relabel, I can say with something which is k steps in the future, is a good goal, you know. So that strategy, works quite well. And, there's comparison of, DDPG, which is the baseline they compared against. And you see, this dash red line performs very poorly on these tasks because the rewards are very sparse, versus DDPG plus HER, which is hindsight experience replay, ends up doing a whole lot better. Okay, so let's see. So, a question which has come up is, does hindsight experience replay distinguish the true goal and the pseudo goal? No, it does not. Right? And what you're evaluating is the performance on the true goal, but in the training process, you're not distinguishing between the pseudo goal and the true goal. So turns out, this paper did not mention it, but how you choose the goals and how many goals you choose, that can really affect the performance of HER. Right? This is something which, is a practical thing that you would see when you implement HER. Now, another question which has come up is, should HER have more variance? So there are two things which are happening, right? So if you see, so one thing which is happening is because you have to do many more goals, you should have higher variance because of that. But you're also getting much more denser reward, which is going to cancel out the variance, right? So it's a trade-off over here, right? So it's hard to say a priori whether it will increase variance or not increase variance. So I would, end this lecture with a small discussion, which is on how to actually specify a goal. Right? So we have been discussing about, so we started with inverse models and we built up to goal condition RL. Right? So one way to specify a goal is to just, for example, give an image of how things are, right? For example, I can have this image showing objects on the left, and I can, have an image saying how the object should be. So if I'm trying to rearrange objects, maybe this is an appropriate way of stating the goal. But what about, if I take coffee, I pour it in the other cup and then I keep the cup, right? Then if I look at the final image, it might not tell me much, especially if I'm looking from the side view, right? I mean, both cups would look the same. So I wouldn't know just from the goal image what the task was. Then you might say, well, instead of just giving me the last state, how about I give you a video, right? Which, for example, this video I'm reusing from our imitation learning lectures where I'm, pouring in water. But as you remember, the problem with giving a video is now I don't know what is the important feature to focus on. Should I call the goal state, I am close to the goal state when my hand is moving in the same way? Or should I call that I am in the goal state when the water has poured out, right? So how to define this function, right? Or how to automatically infer I am close to the goal can be non-trivial in the real world, right? So that is one caveat which you should remember when you're using goal conditioned policies, right? And the other thing over here is how do you specify the goal, right? So you can, for some tasks, an image is appropriate. For other tasks, the video is necessary. But as you expand the definition of a goal, you can also run into the issue that there's a lot more spurious information that you might need to neglect, right? Then you might say, well, the way to neglect the spurious information is to maybe give language instruction, right? I mean, move the cup, shift the book, reorient the bottle. But then you run into an issue of how do I actually ground these things into actions, right? So there is no, what I'll leave you with is a thought that there's no clear-cut answer to what is the right goal representation for every task. This answer actually depends on what you're trying to do. So while goal condition RL helps you solve more tasks or generalize to new tasks, the caveat is you have to be careful in how you specify the goal. And if you're expecting the agent will automatically figure out whether it is at the goal or not, that can also be challenging. Right? So with that, I'm going to stop and take any questions that you might have.